Let's talk about physics. Yes, from cosmology and the universe to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
Hello, I am Anya. Welcome to our show. Let's talk about physics.
Hello, I am Mateo. Welcome to our show. Let's talk about physics.
In the 12th episode of this series, let's talk about vacuums.
The original vacuum concept was just an empty place. Physicists thought waves needed a medium for propagation, so they invented the ether. Then Maxwell's equations showed light can travel through vacuum. Einstein's relativity kicked the ether out of the vacuum. This is the classical cosmological vacuum. But Dirac introduced the Dirac sea for quantum states. Now, the quantum vacuum is like boiling water. Particle-antiparticle pairs pop in and out of existence.
Anya, I agree with you.
The cosmological vacuum was once thought to be empty, until the universe's expansion was discovered. Physicists then imagined it filled with dark energy, a mysterious entity driving the cosmos. Quantum physicists soon proposed that cosmological and quantum vacuums were the same. Yet, there's far less dark energy in the cosmological vacuum than zero-point energy in the quantum one. Recently, Professor Grave de Peralta suggested the cosmological vacuum is classical, due to its massive associated mass. This mass is much larger than the Planck mass, confirming our understanding of a classical universe.
Dear Mateo, you are well informed.
Imagine a boundary where classical and quantum worlds meet, the Planck mass. This frontier suggests that large objects, like galaxies, must be classical. So, the vast cosmic vacuum is classical, almost empty, and governed by relativity. This implies quantum vacuums have limited energy, tied to Planck mass particles, a universe where the smallest scales define the largest realms, the cosmic dance of relativity and quantum mechanics in perfect harmony, a frontier that confirms our intuition about the universe, where classical rules reign over the vastness of space, and quantum limits shape the energy of the void.
Anya, I agree with you.
Dirac created the Dirac's sea to make sense of exotic quantum states. The Dirac's sea is the set of all the energy states obtained from a relativistic wave equation. All the exotic states were supposed to be occupied by unobservable quantum particles, and all common states were empty. An observable particle appears when a particle jumps from an exotic to a common state. This creates a bubble in the Dirac sea. The bubble is associated with the creation of an antiparticle.
You are correct, Mateo. The Dirac sea concept conducted to modern field theories.
The Dirac sea concept has a problem. How come there are an infinitude of unobservable quantum particles in the quantum vacuum? Theoretical physicists used a mathematical trick called second quantization for transforming quantum waves into quantum fields filling the vacuum. Particle-antiparticle pairs come to ephemeral existence from these fields. But there is a problem. In contrast with reality, field theories predict a universe with equal number of particles and antiparticles.
Anya, you know a lot. Let's summarize our discussion today.
Imagine the modern quantum vacuum, like boiling water, where particle-antiparticle pairs continuously pop in and out of existence. These pairs emerge from quantum fields, only to vanish moments later. But here's the catch. Field theories predict a universe with equal number of particles and antiparticles. Yet, in reality, our universe is dominated by particles. This imbalance is one of the great mysteries of physics. It's like expecting a balanced recipe, but ending up with too much of one ingredient. The quest to understand this cosmic puzzle continues.
Mateo, now we should talk a little bit more about antimatter.
Wait, Anya. No so fast. We will talk about this stuff in future episodes of this series. This is enough for today. Ciao, Anya. I love you and we love our audience. See you in the next episode.